Hi guys, Mr. Anderson here. This is going to be a review for the lessons that we've kind of worked on during the our time away. And we're going to be taking a summative this week, or a closest thing I guess you can to a summative on your second lesson of the week. It's going to be a Google form for you to do. I just want to go through the concepts that you got to know for that. This will be up on Edpuzzle for you to do, just to kind of practice along with me. On your screen, you should see the learning targets that are for this this review, this topic that you're going to be assessed on. So we're going to go through these individually as we go through the lesson. So the first one is you determine if a relation is a function, explain domain and range, evaluated function notation. Those three kind of all go together. I feel like they're very kind of grouped together in those lessons 9 through 11. And then we're going to look at graphing functions using some technology. That's what 4 and 5 are going to look a lot at, graphing using technology. So we'll go through that as well. First learning target that I want to review is determining if a relation is a function. So on our, try to maybe drag this up a little bit for myself. Actually, I want to write something here. So remember, in order for a relation to be a function, recall that a function, actually write like this. In order for a relation to be a function, every input, remember that's your x coordinate, has to have only one output, y coordinate. That's the key, right? So when you're doing these problems, that's going to be your explanation a lot, is it's a function because the input has one output, or it's not a function because the input has more than one output. So let's do an example here of using some of the set notation that we've been working on. So our x's here consist of 1, 2, 3, and 4, and our y's consist of 4, 5, 6, 7, and 8. 5, 6, 7, 8, 9. And we're going to define the functions f and g below. So for our first one, f, so you could possibly see these written in different ways. So here the function is listed as a set of ordered pairs. So it's kind of tough to see. We can also write that using that mapping notation that we did, right? So if I kind of have a map, here are my inputs. Remember, your inputs are your x's. So it'd be 1, 2, 3, and 4. 1, 2, 3, and 4. Then here would be my outputs, which remember are y coordinates. I apologize for the handwriting. I'm trying my best. 7, 5, 6, and 7. And then we can draw arrows to the input to the output. So 1 maps to 7, 2 maps to 5, 3 maps to 6, and 4, I probably don't need to write 7 twice. I'll just erase this 7. I don't need to write it twice. And the 4 maps also to the 7. So you have to, in answering this question of is the relation a function, you got to ask yourself this fact: does every input, so in other words, the inputs here, right? These are our inputs. The x's are inputs. Does it map to one output? In other words, is there one arrow going from the input to the output? The answer to this is yes, right? So this is yes, a function, because every input has one output. Easy. All right. Now we'll do another one here with G. Hide this for a second. So I'll write another way you can see this is written in as a table, just to do another way. So G again is written as an ordered pair. So we can also sometimes see these written as tables. So I'll just write them as an ordered pair in a table, because you guys are probably used to seeing this. Remember, these are inputs. These are outputs. So I have 1, 2, 1, 2, and 3. Remember, inputs are just the x coordinates, and the outputs are the y coordinates: 5, 6, 8, 9, and 7. And so you got to ask yourself, is this relation a function? Well, no, it's not, because 1 maps to 5, but 1 also maps to 8. So the input of 1 has 2 different outputs. Likewise, so does 2, right? 2 maps to a 6, and it also maps to a 9. So this is not a function. The inputs of 1 and 2 have more than one output. So you can be asked this question. It could be written as a table. It could be written with this set notation. It could be written as this with this mapping here. The other way, it could be written as a graph. So you're looking at some graphs, and are these graphs functions? So the easy way to do that, recall, is that vertical line test. Oops, sorry, the vertical line test. Pretty easy to do. So if you have a graph, remember, in order to have to be a function, it's got to be for one input, it's got to be one output. If you're to draw vertical lines through the graph, right, the vertical lines can only intersect at one point, right? Because that means that there's only one output for every input. So because this parabola, every vertical line you would draw would cross at one point, this is a function. So this is yes. I'm sorry, guys. I'm trying to use some of my new tools here. And so this is yes. Again, every input has one output. That's like always your explanation. One output. Output. There you go. All right, how about this one over here? Let's do the vertical line test on this function. We can see just if I go down through it, right, it crosses here and here, right? So this vertical line crosses at 2 spots, which means this is not a function. Not a function. You can either say thing. You can say fails a vertical line test if you want. Fails vertical line test. Or you can say, again, every input does not have one output. Has more than one output. There's the inputs with more than one output. All right. Next topic is domain and range. So a couple things to review from here is that domain are the set of inputs. You got to think of inputs as the x coordinates typically, and the range is the set of outputs, typically y. So when you're listed in a set form like this, it's very easily the domain is just the x coordinates 1, 3, and 7. So 1, 3, and 7. These curly brackets just means that's a set of those numbers. And then for the range, it's the y coordinates. So 2, 5, and 9. So 2, 5, and 9. This is a function because, again, every input 1 has one output. 1 gets you 2, 3 gets you 5, 7 gets you 9. 1 doesn't give you another number, right? 3 doesn't give you another number. It only gives you 5. 7 only gives you 9. So that's pretty simple, right? When the functions are listed in set notation. This is where it gets a little bit tricky, is in general algebra problems. So here we have a function. This is a linear function. So remember, the domain are your inputs. That's what values of x you can put into the function, right? And think about a linear function. It doesn't matter what number x is, right? This is a line, right? I'm multiplying x times 3 and then subtracting 2. I can multiply any number by 3, then subtract 2. So when we say it doesn't matter, it could be any number, we say the domain is all real numbers. And there is a symbol for that, if you recall. It's this R with a line down like this. This symbol is another way to write out this phrase. Okay. And then the range, again, if you think about this is a line, right? This is a linear function, as you guys know. So the linear is going to go up forever and down forever. It's going to go up, and it's going to go down. It's going to hit every y coordinates. This is also all real numbers. Okay. Now, this is where it gets tricky, but you guys have technology at home, so you can be using technology to help yourself out a little bit. So g is x, g of x, this next function is g of x equals x squared. All right, so we'll think about the domain first, because that might be easier for us to think about. Again, you're squaring a number. So again, the domain is x's. What values of x can I have here if I'm squaring a number? What numbers can I square? The answer is that I can square any number, right? Negative, positive, irrational, rational. It doesn't matter. I can square any number. 3 squared is 9. Negative 3 squared is 9. So this, again, is all real numbers. The range, this is where it gets a little bit tricky. Now, you can use technology to help you, which I'll show you in a second, but we also can think of it mentally. I'm squaring a number, right? So I can either have three options. I either can square 0 squared, which would be 0. I could square a positive number, right, which will stay positive, right? 3 squared, 3 times 3 is 3. Or I can square a negative number. Just putting little quotes around it. So little quotes. I can square a negative number. Well, squaring a negative means I take a negative and I multiply by a negative. That is still positive. So my outputs, my range, are going to be 0 and all of the positive numbers. So how can we write that? Well, it means that our range, our y coordinates, can be greater than or equal to 0, right? Now, if I were to do that on a graphing calculator, create a new blank graph. If I were to graph g of x equals x squared, you can see you get this parabola, and it goes up to the, when you go to the left, you can see how it's going up, and it's coming down, and it goes back up. Like, it's never negative, right? This graph is never crossing over the x-axis. Now it will go left and right forever, so our domain is the x, all real numbers, but the range, the y's, are always going to be positive. All right, one more here. Again, we can use the graph to help us. If you get stuck, you can always do that, type it into decimals and analyze it. All right, so here we're doing the square root of x. So remember, square root means what number times itself gets you what's inside of it. So what numbers can I square root? Well, I can square root a positive number, right? For example, the square root of 9 is 3. That works. I can square root 0, right? That's 0. Can I square root a negative number like negative 9? Well, I can't, because there's no number that when you multiply by itself, no real number, I get negative 9. I can't do this. So the domain is not all real numbers here. The domain is x is greater than or equal to 0. In other words, I can square root 0 and any number greater than 0. All right, now about the range. Let's look at the range of this graph. So we're going to make a new function. H of x equals, oh, of course. I'm going to write it a different way because my, oh, there we go, I'm good. The square root of x, was it minus 3, I think, right? Yeah, minus 3. Minus 3. All right, there's what that graph looks like. And you can see the x's, I'm not crossing over to negative, right? These x's are all, this graph has all positive x coordinates, okay? All positive x coordinates, all right? So it's never over here, right? The graph is never on this side. It's greater than or equal, the x's are greater than or equal to 0. Now, what about the range, the y coordinates? Well, what's the smallest it could be? Well, right here, right? It could be down at -3, but as you can see, this graph is increasing constantly. So it's going to go all the way up to infinity. It's just going to constantly increase, but it's never going to be below -3. So the range is going to be y is greater than or equal to -3. If you think about the subtract 3 there, that's how another shortcut to get that. All right. Next topic. This one's easy. Evaluating function notation. So I can use function notation to evaluate inputs. So I have two functions here. I got f of 2, I got f of x, which is 6x minus 3, and I got g of x, which is 2 to the x plus 4. So all we do with function notation is we just, wherever we see an x, we replace it with what's inside here. So we have f of 2. I'm going to replace the x with 2. All right, and I'm just going to evaluate it. It's do order of operations. So 6 times 2 is 12, minus 3 is 9. So there's f of 2. For g of 3, again, I'm going to replace wherever I see x, I'm going to put a 3 in. So for g of 3, I'm going to do 2 to the third power plus 4. So order of operations, got to do exponents first. I'm going to go up here a little bit, get out of my way. So 2 to the third power is 8 plus 4. I get 12 for that one. F of 0, so again, I'm going to put 0 in for x. I get 6 times 0 minus 3. 6 times 0 is 0 minus 3 is -3. Last one, try to trick you here. G of -1, I get 2 to the negative first power plus 4. What is this, right? Well, this is the same as 1 over 2 to the positive 1 power plus 4. And then 2 to the first power is 1/2 plus 4. This is 4 1/2. The point is, guys, for those problems, you just replace the x with what it tells you, or it could be any letter, but just you put, this is function notation, right? The idea of a function is I put an input into it, I get an output. All right, so this next one is going to be on the graphing part from lesson. This is lesson 14, and I believe lesson 14 is kind of where we did this. So I have this is how your test questions will look. I say using technology. I'm going to have you guys just analyze some graphs. So here's this function, this ugly looking function. I graphed it here on Desmos and copied the image over. And I want us to state an interval where it's increasing. I'm going to do one, and then you're going to make one on Edpuzzle on your own. So you got to look at the graph. Where is the function increasing? Well, where's it going up? Well, here, it's going up here, and then it's going up here, right? Oops, sorry for my awful writing, but you get the idea, right? This part of the graph is going up, and this part of the graph is going up. You just got to come up with any interval on that graph. Doesn't matter. Well, let's think here. Remember, this is going down, right? Technically, forever, and it's going up here forever. And you always read the graph left to right. So, like, this graph will touch every x coordinate, right? It'll hit every x coordinate. So, where's an interval that it's going to be increasing? Well, I'm going to go from. This is the notation we got to use. This bracket notation is different than an ordered pair, then, right? So -2. That means from -2, if I were to draw some, like a dashed line here, between -2 and I'll use -1, make it easy. Between -2 and -1, this graph is increasing, right? All of you guys write down in Edpuzzle a different part. You could have gone over here, right, if you wanted to. Where is it decreasing? I'll do that in a different color. What's decreasing when it's going down in this little part of the graph? So where is it decreasing from on the x coordinate? Well, I'm gonna go make it. I like to use integers, make it easy. It's decreasing between there and there. Between, what is that? Between on x 0 and 1. This, again, these closed brackets means I include 0 and include 1. There's a lot of other ones. You could also do fractions. You could have done 0.5 to 1.5, I think. Yeah, it looks like it. But the interval's got to be between this from this point here down to D, pick any two numbers. Like you guys choose one. All right, then which point is the relative maximum? That's just a maximum. Think of it as a peak of a hill. So where's the peak of a hill? Up here at point B. So the max is at point B. And then the relative minimums, like the peak, or the valley, right? Down here at D is the valley. So the relative min is at point D. Okay. So that's what you got to have to. You're going to see questions very similar like this on the test on Google Forms. One more topic, and that is I can compare growth of linear and exponential functions and analyze real-world situations. This you're going to probably want to know how to use Desmos to do. We've done a lot of modeling this year so far. So what we're going to do is we're going to enter this data into Desmos and see what type of model best represents it. Just get out here so I don't have to flip through the screens. So we're going to go on to Desmos right now. And then we're going to input into the table, which we've done before. I just lost my pen. Oh, here it is. Right? We'll put these values in for X and these values in for Y. Right, so remember on our table, we're going to hit the plus sign, hit table. We're just going to put on the X's 0, 1, 2, 3, 4, 5. And on the Y's, 15,000, 15,600, 16,224, or do not use commas, 16,873, 17,548, 18,250. All right, so then again, we have to see in order to see our graph, remember doing this with the paper folding activity as well, is we're going to have to adjust our window. So for X's, a good X probably to go between is, I think, 0 to 5, make it easy. Go 0 to 6, let's go one more. Let's go by ones. And then for Y, so we'll start probably 15,000. Oops. Then go up to 19,000. Oops. Whoa. Whoa. And step by 500. Right, so there's our data. So what's really what your job is to look at the data set that I give you and think about, well, what model best represents the situation? Does a linear model best represent the situation, or a exponential? So if I look at this data, to me, this data is clearly increasing at a linear rate, right? Doesn't have that exponential growth curve at all. It's increasing at a linear rate. So I'll write this down over here for you, the two options. So if you determine it's linear, which we have here, what you'll type into Desmos is this: y1 tilde m x1 plus b, right? If you determine it's exponential, I think the one on the lesson you did was exponential, remember. You type in y1 not equals, tilde, right? Tilde a times b. I'm sorry, guys, it's a stupid pen. A times b. Jeez. Gotta be very sensitive here. A times b to the x1. Okay? So you have to use an exponent tool and just hit x1. Those are the two models you type in. But we've determined it's linear, so we're going to type in that first one. So we're going to go to Desmos. We're going to hit y1 tilde mx1 plus b. You can see it's very linear. See that high correlation coefficient we talked about before. And then we're going to write down the models. So remember, we have to replace these letters in for the letters in our equation that we or our model that we typed in. We got to replace the m and b into b. So we'll go back to notebook and we'll do that. So write a function that closely matches this. So we'll do that down here. So we'll say f of x equals 649.8 x plus 14,958. Okay, there's A. Then B is usually going to have to use your function to make a prediction. Assume the function is good at modeling growth between 2012 and 2032. In what year, the time frame, was the water supply be inadequate for the population? I didn't read the question. Probably should have done that. So basically, you had to determine when this model is greater, when this number has become greater than 30,000, it looks like, right? So the water's good up to 30,000. So we put 30,000 in for our output. Right? How many years will it take to basically be over 30,000? And then we're going to solve it for x. So we're just going to, oops, got my x here. Oh, geez, my handwriting. X, forgot the x. All right, so we're going to subtract 14,958. And we get, on the left here, we get 15,000, what is that, 42 equals 649.8x. And we'll divide by 649.8. I get x equals, what is that? 15,042 divided by 600, what was it, 649.8. You get 23.1. years. And so do a little calculation. This is from the year 2007, right? Time 0 is 2007. So we'll take, to see what year that is, we'll take 2007 and we'll add 23.1 to it. Right? So it'll be the year 2030.1. So the year, if you go on past 2030, it means it'd be the year 2031, you'd run out of water, right? So the year 2031, you'd run out of water. Pretty close to the end here, but that's how you would do that problem. The point is, guys, looking at the data to determine what type of model is best is important in that, and then typing in the model, making a prediction, stuff that we've done. I believe that's it. Yep. So going back to all the learning targets that you need to know, that's what they are. Hopefully this video helps. You can work along with it on Decimo or on Edpuzzle. And best of luck to you. Stay healthy.